Okay, so this class is going to be a little bit shorter. Something that I try to do between the two sections is to keep the two sections at the same pace. And the others, this section, we went a little bit farther away on Wednesday. So chances are that in order to keep you guys at the same pace, this one is going to end shorter. Not a lot. I'm not saying that we're going to have an hour earlier, maybe 10 minutes, something like that. That just want you guys to know. Okay. So you guys were on most of you were online on Wednesday. So is there anything you want me to go over again that it didn't make sense or that you couldn't see the images or for whatever reason? Anything that you want me to go through? Akina? I know you were here. Mm-hmm. You should not have any questions. I don't. Everything was perfect clear. No? Kayla? Karim? Karim. It's going to take me a while. Okay, so one of the things that we want to do with all these vector operations is that we want to do some very basic arithmetic operations with vectors. We want to be able to add the vectors, we want to be able to subtract them, and we want to multiply them or magnify vectors, okay? So all these exercises that we're doing right now is precisely to be able to do that, to know how to manipulate, from the point of view of math, how to manipulate the vectors, okay? Next week, we're gonna start applying the vectors to more tangible examples, okay? So yesterday and today is just a little bit of math. And also for you guys to remember your trigonometry functions and all that stuff. Okay, so what we did, the last thing that we did on class on Wednesday was to find the components of a vector. So we start Wednesday by giving you the components, giving you the coordinates of a vector, and then trying to find what is the magnitude and what is the direction of that vector. And now what we're trying to do is do the opposite. So we have the magnitude and we have the direction, and then we try to find the components. The thing that is important to notice is that if you use the math just straight from your calculator, it's going to give you values, and the values, the magnitude of the value may be correct, but you need to look at your drawing, you need to look at your diagram, and then look at, okay, this vector is on the second quadrant. So that's going to imply that you have a negative x component, that you're going to have a positive y component. So you need to match your result to reflect that. So you need to have your negative x component and your positive y component. Okay, this is not something that your calculator will give you right away, especially how we are working with the angles. So you need to do that outside the calculation, outside the calculator. Okay. Okay, makes sense? Okay, so let's do one quick example. Okay, so one of the things that we want to do is to do a simple operation like I have two vectors, A and B, and I want to find what is the resultant vector, AB equals C. We have scalars, well, this is 3 plus 5, there will be 8, and that's it. There's nothing else. However, with vectors, it's a little bit different. We have two vectors, and let's say vector A has a magnitude of 20 units and an angle of 20 degrees, and vector B has 20 units of magnitude at an angle of 40 degrees. We cannot do something like this. This will be wrong. We cannot do that. You cannot add vectors, just the magnitude and then just the angles. It doesn't work like that. The way you have to do it is that, okay, I have my vector A, and then I need to find where are the components. Oh, crap. Give me a minute, okay. I forgot to share my screen, so I'm talking, I didn't see anything. There you go. Okay, so you have one vector, 20 units, 20 degrees. You have another vector, 40 units of magnitude, 40 degrees. You cannot just add them and end up with a vector that's 60 units, 60 degrees. The way you do it is you have a vector A and you need to decompose it in the X and Y components. Sorry. You decompose it in X and Y components. You do the same with vector B. So you have your X and you have your Y components. And then your vector C will be the X components added together and then the Y components together. So you will have AX plus BX, AY plus BY. Now you end up with the components of C, and then you can use those components to calculate the magnitude and calculate the direction of B. Okay? So it's a little bit complicated. It's a lot of steps. But right now, with the algebra that we have, that's the only way we can do it. Okay? Okay, so we're gonna do this example. So let's say that I have vector A, 20 units at 20 degrees. And now these angles, I'm assuming that I will respect with the X, positive X. So the positive X axis. So, and vector B will be 40 at 40 degrees. So I will have A will be something like this. It will be vector A, and vector B will be something like that. Okay, so now what I'm gonna do is these first two rows, calculate the X and Y components of vector A, and these two rows, calculate the X and Y components of vector B. And on the chat, I don't even know who's in there. Wait. Yeah, so for the people that are online, some of you want to do A and then post, put the result on the chat, and then someone else can do B, just so everybody can double check their values. Or if you want to do both, that's perfectly fine. That's a good practice anyway. Oh, crap. I forgot my calculator. is super weird because I'm screening the what is in this there in the phone, and then you see my phone, and then the phone. It's like Inception, but okay, I should stop. Okay, come. Okay, I'm gonna go for my calculator. Okay, Grace, are you done? Okay, so what you got for the x components of A? 18.8, and for the y components? 6.84. Okay. Michaela, what you got for the x component of B?
30.64.
And for y?
25.7.
Okay. Does everybody got those results? More or less? Okay. So now you decompose vector A and vector B, and now we can add them. So if I want to add and obtain vector C, then I add the x components with the x components, and then the y components with the y components. So I end up with 49.44 and 3.25. No, 32.54. Okay. Now those are the components of vector C. Now we need to calculate the magnitude of C, and we need to calculate the direction of C. So the magnitude of C will be 49.4 square plus 32.54 square. I get 59.2, and then the direction, that's going to be the arctangent of 32.54 over 49.44. That's going to be 33.4 degrees. Okay, so if we look at our original diagram, 33.4. So our first vector A is at 20 degrees, vector B is at 40 degrees, so vector C is going to be somewhere in between. And the magnitude is going to be almost 60, so it's going to be much, well, it's going to be bigger than B. So that will be our vector C, somewhere around there. Yep. Make sense? You want to try another one? Okay, so okay, so those are the two vectors. We have vector A and vector C. Vector A has a magnitude of 30 at an angle of 20 degrees. But the 20 degrees is 20 degrees below the positive x-axis. So that will be this will be theta A. And for vector B, we have 40 units at 35 degrees below the negative x-axis. So that will be, these will be theta B. And again, what I want to calculate is what is vector C as the sum of the two vectors. So be careful with your signs. Look at where the vectors are. You have one vector in the fourth quadrant, another one in the fifth quadrant. So what will be the sign of the x and the y component to be in those quadrants? So if you just put those numbers in the calculator, it's always going to give you a positive value. But that's not necessarily the case in this example. Okay, so I'm going to do, some people on the chat, they want me to go through, calculate really quick the components. So I'm going to do the components of vector A. So for vector A, I'm going to extend this axis, and I'm going to assume that what you have here is a triangle rectangle. I'm going to have this triangle over here. So I'm going to draw it. This is theta A. This is the magnitude of vector A. That's going to be the 30 units. And then what I need to find out is the y component and the x component. Okay. So the x component is the adjacent side to the angle, and the y component is the opposite side of this angle. So I'm gonna say, okay, sine of theta A is opposite of the hypotenuse. So delta y over the hypotenuse. And cosine of the angle is gonna be the adjacent over the hypotenuse, and the adjacent is gonna be the angle x, I mean the component x. So from here, the y component is going to be the magnitude sine of the angle. This will be 30 sine of 20, and that's going to be equals to 28.2. Is that what you guys got? And for the x component, I'm going to have 30. No, this is 10.26. And for this one, will be 30 cosine of 20, and this will be 28.2. Now, the problem here is that the calculator gives me positive values, but because vector A is in the 4th quadrant, the y has to be negative. So this is going to be negative 10.26. Yeah? Morgan, does that make sense? Okay, anyone else in the chat? Any more questions? Okay. So you have to do something similar, but with vector B. Yes.
No matter which way the vector is pointing, will sine always be for like the y component and cosine always be for the x component?
No. It depends on where you define your angle. In this particular case, because we are defining the angle here, then the opposite will be y and the adjacent will be x. But for example, if I had the same vector, but I give you this angle over here, and then you can find the components. But now, because you're working with this angle, this delta x, sorry, the x component is going to be the opposite, and y will be the adjacent. So it depends what angle you have. So we'll do a couple of problems like that, so you get used to it. But no, don't think that x is always going to be cosine and y is always going to be sine. It's not, doesn't work like that. Okay. Anyone? Kaylee? Do you have B? Kayla, you have B? You have the components for B?
For B, I think for Y, or for the X one, I got 22.94, and then for the Y, I got 32.
32.
I didn't write that. I got opposite.
Yeah, I got that.
Oh, okay. 32.77.
30.77 and 22.94.
Yeah, negatives.
Oh yeah, and these two have to be negative because they're in the 4th quadrant. So because they're in the 3rd quadrant, so they have to be, both they have to be negative. Okay, so oh, I need more paper. Okay, so we got this vector A, the component is 22.8, and Y will be minus 10.26. And for vector B, we have minus 32.77, and for the Y component, minus 22.94. Yeah? Okay, so vector C, we'll just add them together. So for the first one, we have negative 4.56. And for this one, we have negative 33. Oh, crap. $33.2. Okay, I can calculate the magnitude. It will be 33.51, and I can calculate the angle. And I get an angle of 81 degrees. Okay, I'm gonna try to draw this vector just to figure out where it is. Okay, so if I just look at the components, I have my X component to be negative 4.6, so it's gonna be something like that. And then the Y component is negative 33, so it's gonna be way down here. So my vector is gonna look something like that. Very long and very close to the negative Y axis. So this angle, the 81.94, is almost 90, so it's gonna be this one. That's the angle that I'm finding. Okay, so my recommendation is that every time you try to do these problems, we're going to be working a lot with vectors. So every time you work with vectors, try to set the vectors in a reference point, in a Cartesian plane, and try to draw where the vectors are. And then when you do operations, then you can try to figure out if your result makes sense, depending on where you expect it to be. You know, you may have an idea, okay, if I have two forces pushing to the left, to the right, sorry, you have two forces pushing to the right, then if I add them together, well, the force can also be pushing to the right. There's no way I can end up with a force pushing to the other side. So you can more or less evaluate if your result is fine, is correct. But it helps if you do the drawing. Okay. Make sense? People in the chat, they work. Make sense? Make sense? Yep. So there's a question, like if the angle is always measured with respect of the x-axis. No, you can measure angles anywhere you want. you can measure the angle with respect to the x-axis. You can measure this angle with respect to the y-axis, so this angle will be 8 degrees or something. You can measure an angle from the positive x-axis, and it will be something like this. Or you can measure the opposite angle, and it will be something like that. All of them are correct. All of them are fine, which that's one of the reasons that makes working with vectors a little bit confusing. I personally prefer to work either with the positive x-axis or the negative x-axis. And whatever gives me less than 90 degrees, I work with that angle. So in this particular case, I'm not gonna be working with the positive x-axis because this angle is huge and this angle is bigger than 90 degrees. I'm not gonna be working with the y-axis. I'm sorry. So I'll be working with the negative x-axis, and I'm gonna try to pick the angle that is less than 90 degrees. Okay, it's just my preference. I don't like working with angles bigger than 90 degrees. I'm lazy that way. I just don't like it. But in general, you can define your angle any way you want. I will say make your life easy and work with angles less than 90 degrees and try to use the x-axis. In some cases, we're going to be rotating axes, and sometimes the axes are continuously changing, and then you don't have any option. But in these particular cases, work with the x-axis, pick the one that is less than 90 degrees, and you're good to go. Okay? You were yawning. I see you. I saw you yawning. Okay. Okay. Oh, what happened? Okay. Can everybody see me? Well, then. Okay, so we're gonna stop a little bit with the calculations here, and we're gonna start with chapter 4. Chapter 3, if you look at your textbook, chapter 3 talks a little bit more about velocity and acceleration. It talks about circular motion and a bunch of other stuff. We're not gonna deal with motion until almost the end of the semester. All those problems of throwing the ball and the parabolic trajectory and all that stuff, we're not gonna be dealing with that right now. We're gonna skip that part, and we're gonna deal with forces. And we're gonna be talking about forces, equilibrium, and torque. And hopefully that will be the first topics for your first exam. So in terms of chapter of the book, we did chapter 3, so we're gonna do for chapter 4 and 5, and then we're gonna skip to chapter 8, and we'll see where we are in a couple of weeks. But that's gonna be more or less the sequence that we're gonna follow. Chapter 3, 4, 5, and 8. So that's hopefully that's gonna be your first exam. Okay. Okay, so we're going to be dealing with forces, and everybody, we all have an idea or a couple of concepts of what a force is, because we have experienced forces one way and another. So, Alex, do you like to be called Alex?
Yeah.
Okay. What do you know about forces? What do you think our forces are?
Forces are things that are able to act on another, so to be able to like create movement.
Create movement, yes. So I'm going to try to put here. Oops, oh, I can't. So forces create movement. Movement. Did I spell it correctly? Yeah. So forces create movement. If something is moving, it's because at one point a force was applied to that object. Okay? Nothing moves just because it decides to move on itself. There's always a force that is being applied, and that thing starts moving. McKenna. Am I pronouncing your name correctly?
McKenna.
McKenna. Okay. McKenna. I'm gonna try to remember. What else? What else do we know about forces? Well, I mean, I know we haven't read anything about forces, and we are a little bit ahead of the topic. But what you perceive about what a force is?
More than one force can be applied to something at one time, but you don't just have one.
Yep. Yeah. Force. So multiple forces can be applied at the same time. If people in the chat have any idea or any suggestion, they can just write on the chat. Mary.
Yes.
Yes. What else?
Well, when we're on Earth, like gravity is a constant force that we have to deal with.
Gravity is not a force, but you are correct. I mean, we're gonna put something gravity here. I'm just gonna put it here. Okay, gravity is not a force, but yes, it's something that is acting on us all the time. Ian. No, sorry, Donnie. Brian. There's an Ian in the morning session. A force is a vector. So forces are vectors. So we need magnitude and direction. Next to Donnie, Brian. Who's Donnie? You, Chris. Okay, who's Donnie? Okay, Chris. What else?
Multiple forces.
There are multiple kind of forces, the different kind of forces. We'll talk about like why, what kind of forces you think they are.
Sure. I mean, there's different forces on different types of elements. I guess.
You just wing it.
I kind of.
That's okay. In front of Chris, your name? Rihanna. Okay. Anything? Nothing? Are you gonna even try?
That's all I got is up there.
Oh. On the back, Kaylee.
So when you apply force, it's also a force pushing back on you?
Yeah. So we'll talk about that. You're a little bit ahead, but that's fine. So one of the things that you need to understand is that forces are always going to be either a push or a pull. That's the two options that we have. There's going to be a push or pull. And there's always going to be an object that applied the force, and there has to be an object that received the force. Okay? So you cannot just apply a force to nothing. It has to be something that received that force. And there has to be something that creates that force. Okay? So there's always going to be something that creates the force. And something that receives. And I'm going to put a kind of like a mark there. Forces are always going to be in pairs. So when I push the wall is pushing me. So even though I am creating the force, and the wall is the one that is receiving the force, and I push it, at the same time, the wall is going to be pushing me. And it's going to be pushing with the same amount of force, just opposite direction. So forces always appear in pairs. So if I push one direction, the wall is going to push me back in the opposite direction. So there's always going to be in pairs. Okay, now the other thing is that this is not very obvious, but there are two kinds of forces. Forces that are in contact, like me pushing a wall or lifting an object. This is forces that are in contact. A football player tackling someone. And there are forces that can be applied on a range. For example, gravity, or the effects of gravity on a mass. So gravity is created by the mass of the Earth and is pulling objects to the Earth. At the same time, the object pulls the Earth up, but because the difference in mass, we don't notice. But even though the Earth is not in contact with the pen, well, the pen falls. And it falls because it feels that force of attraction. Okay. The other example are magnets. So if you have two magnets, opposite polarization, and you put them close, you start to bring closer and closer together, even though they are not in contact, eventually they pull each other, and there's a force, there's a magnetic force there. So not all forces you have to be in contact. There are forces that can be applied at long range. Okay. Now, Mary mentioned gravity. And she said, like, oh, gravity is a force. And it's not necessarily true. It's partially correct. It's not completely wrong, but it's not completely right. So we have weight. And weight is a force. And weight is the force created by gravity. In this case, the gravity created by Earth. On a particular mass. So if you have mass, and that mass is close to the Earth, that mass is going to have some weight. And that weight is going to be a vector, and that vector is basically pointing down towards Earth. Okay, so weight is a kind of vector, and it's kind of vector, a force that we're going to be working pretty often. Other type of force are springs. Now, when I say, Grace, when I say spring, what do you think? Something bouncing, what shape? Yeah, so most people think about something like this, kind of like a metallic coil that can be compressed or extend. And then you remove the force that is extending the spring, and it goes back to its natural shape. Now, this is a very engineering physics way to see springs. In reality, anything that you can imagine that can be deformed, and when you release the force, it goes back to a natural shape, that can be modeled as a spring. So if you have a piece of wood and then you bend it, I'm not going to bend it too hard. So if you bend it and then you release and it goes back being straight, this is a spring. Your skin, you pinch your skin and you lift your skin and it goes back to its natural position, unless you are really, really old and it just stays all crunkled. But you guys, you pull your skin and it goes back to a natural position. That's an elastic material that behaves as a spring, or it can be modeled with a spring. Your tendons, your muscles, your cartilage, all those can be modeled as springs. Okay, so we'll talk about springs sometime later, but that's a very, very, don't think just of those metallic coils. Tension is another kind of force. So this is a little bit of what Christopher was saying, that there are different kind of forces. So yes, there are different kind of forces depending on what creates a force. Tension is a force that can only pull an object. It's only a pull force. And it's a force that is created by strings or ropes or wires. Basically, objects very long with a and very thin. Those creates tension, and tension is a particular kind of force because you cannot push with a rope. Okay, that's the main difference. Like you cannot push with a wire. You can only pull. Okay, so that's where we will make a distinction between this particular kind of force. Is the object that creates the force. Okay, another force that is gonna be we're gonna be talking about very common is called normal force. This word normal is a mathematical term that it means perpendicular. Okay, and this is a force that appears when you have an object in contact with a surface. So every time you have an object in contact with a surface, you're gonna have the normal force. So if you have a box sitting on the floor, just the contact is gonna create a normal force. So weight is gonna be pulling down, it's gonna make in contact with the ground, and then the ground is gonna push back. That pushback, that's the normal force. And it's always gonna be perpendicular to the surface. So if the surface is horizontal, the normal force is gonna be like this. But if you have an object sliding on a plane, or just sit on the plane, the normal force is going to be perpendicular to the plane. If you are in a roller coaster and you are somewhere on the top, the normal force is going to go down. Okay, so the key issue here is that normal force is always going to be perpendicular to the surface. Okay. The next two are kind of similar. Friction and drag. Alex, what do you know about friction or drag?
Friction is when you is between usually two objects or different types of matter, and so it's in the way I think of this when I describe stretchers off, you use the word drag because as they move across each other, they either have, depending on how like smooth or porous the surfaces, they'll have more or less friction or drag.
So what will be the difference between friction and drag?
I guess I think of drag as always being like a pull like force when something becomes dragged. I'm not really sure though.
The back.
The friction is created from dragging? I don't know.
Okay, so close. Yes. So friction always happens when you have two surfaces sliding one respect of the other. Okay, so you have a box slide on the floor, you're gonna have friction. You have you throw someone on ice, that's gonna be some friction. And depending on the quality of the material, how smooth and how wet and many other things, the friction can be increased or can decrease. Yes. And drag is what happens when we move something through a fluid. Yes, that's the main difference. So friction is between two surfaces, and drag is caused by when something moves into a fluid, there's going to be a displacement of that fluid, and that displacement is going to slow you down. Now, when we think about fluids, or when I say fluid, I don't necessarily mean liquids. A gas is a fluid. Water is a fluid. But if you are, have you ever played in those pools with balls? And you try to run that thing, and you can't. It's hard. So those balls, even though are solid, they behave as a fluid. Or if you have rice in your pantry, and then you put your hands in the rice, and you feel that hand moving in the rice but very slow. Or if you are in sand, playing with the sand, the rice, and the grains, they behave like fluids. So, so the drag is basically that motion that prevents for you to move smooth through any of those materials. Now, the key with friction and drag is that always gonna oppose motion. They're always gonna slow you down. You cannot have friction that's gonna help you move faster. You're not gonna have drag that's gonna move you faster. You, John, again. Twice. Make sense? The last one is thrust. And thrust happens when you have some kind of push through a fluid. Thrust always going to be a push force, and that's it. That's all the forces that we're going to be talking about. There are some forces that are going to be talking more than others. Normal force, weight, spring, friction, those are going to be the forces that we're going to deal in most of the time. Drag, a little bit. Thrust, probably not. Okay? Make sense? Questions? You're ready to go. It's Friday. We made it, week 1. I don't know how long we're going to be open, but at least we made it to week 1. We beat CMU. A couple of things. There's a quiz due on Monday. It's about chapter 4. We cover most of chapter 4. The only thing that is missing is a little more specifications of these forces that we just talked about. But we pretty much finished chapter 4. So don't forget your quiz. There's a homework due next Friday. So make sure that you have access to that homework. And if you have any questions, just let me know. Mary, shall we leave or shall we stay? We should go? Okay, Mary just tell us to leave. So let's go. See you guys next week.
Have a good weekend.
Thank you too.
So I've been working on the doctor's homework all week. I
Okay.
do math very slowly. In the end, if you